Good evening and happy Wednesday after a long holiday weekend. First test was due at 6 p.m., so that's out of the way. We now begin a more in-depth study of the different types of functions we have. We start by looking at polynomial functions and rational functions. Tonight is going to be mainly review of basic algebra. And tonight's plan is to go over the complex number system and the quadratic polynomials, right? Quadratic functions. Tomorrow night is when we'll look more in depth at polynomials. So in mathematics, we work in number systems, right? Specific sets of numbers. The base of our number system, the starting point, what is known as the natural numbers. Just seeing that. May also hear these referred to as the counting numbers. So I'm going to put 0 in green because depending on the text you're looking at, 0 may or may not be included in the counting numbers. I personally don't count 0 as a natural number. Right, so I personally define the natural numbers as the numbers 1, 2, 3, 4, 5, 6, right, so on and so forth, right? It's the numbers that you actually count with. We typically don't count with 0. After the naturals, we have the integers. And the integers are the natural numbers, they're negatives, and 0. After the integers, we have what are called the rational numbers. All right, so rational numbers are defined as an integer over a non-zero integer. So it's the set of all those numbers. Right, so 2/3, 1/2. 6/7, 13 halves. Those are all integers. Oh, I'm sorry, those are all rational numbers. And as a little note, if you have a decimal that terminates, it's rational. As well as any decimal number where the digits of the decimal start to repeat. Right? So 0.999, it terminates. So that would be a rational number. 0.3 repeating. It constantly repeats, so that would be rational. As long as it terminates, it's rational. So there could be 100 million of these nines. It terminates after 100 million, that's rational. This decimal, 0.1235, and then 468, 468, 468 repeats like that indefinitely, that's rational. And as another interesting note, the decimal 0.9 repeating is equal to 1. That is very simple to show. In fact, I think I will show it. Let x be 0.9 repeating. This means that 10x would be 9.9 repeating, right? So if you subtract the two, right, 10x minus x, that's 9x. But that would have to be 9.9 repeating minus 0.9 repeating, which is 9. Which means x has to be 1. Only works because the 9 repeating goes on forever. Then we have the number system that we work the most in. In fact, it's the number system you've been working in your entire math career. These are the real numbers. Then we have the complex numbers. It's the set of all numbers that can be written in the form of a plus bi, such that both a and b are real numbers, and I squared is -1. Meaning I would be root -1. A is called the real component of z and is written as RE of z. B is called the imaginary component of z, and it's written as IM of z, read imaginary of z. So what makes the complex numbers now so important? I'm so glad you asked. Right. We no longer call these imaginary numbers, right? We call them complex numbers. Because as it turns out, a lot of the solutions from quantum mechanics, and when I say a lot, I mean probably over 75% of solutions from quantum mechanics are complex. They involve I. Well, considering that quantum mechanics describes is the physics of the very small, so like, the atoms, and our entire universe is made up of atoms. Our entire universe is basically explained using complex numbers. Well, this opens up a whole new branch of mathematics. Right? A lot of the functions we deal with are what are called real valued functions. And in fact, the entire calculus sequence deals with real valued functions. But we can also have complex valued. I have studied quantum mechanics. The very basics of it. I took quantum 1 and quantum 2 in my physics undergrad. You're not going to like my answer. I was born with it. It's just been innate for me. I've always been good with math. Right. Another answer is I've also been doing this for like 30 years. So you may not be born with the innate ability to do math, but if you put in the time, you will get good at it. It's the beautiful thing about math. Complex valued functions. Quantum mechanics would be used when you're dealing with when you're trying to describe anything that on the atomic level. So if you study any kind of particle theory, that's quantum mechanics. Or it's part of quantum mechanics. It's an application of quantum. Chemistry is technically an application of quantum mechanics, right? Because chemistry deals with atoms and molecules and things like that, and that's all governed by the laws of quantum. So complex functions, you're not going to deal with those, at least not for a while. Math majors definitely going to have to deal with it. It's a senior level math course, complex analysis, which is essentially calculus, but on complex valued functions instead. Physics, obviously, if you're a physics major, you're going to have to deal with complex valued functions. I was just discussing quantum. And I think certain branches of engineers also have to deal with it. Thermodynamics involves quantum, which involves the complex numbers and the complex valued functions. But that's not for a way off yet. Now, the interesting thing about complex numbers is we can imagine each complex number as an ordered pair and plot it on an axis called the complex plane. On the complex plane, the horizontal axis is called our real axis. The vertical axis, is called our imaginary axis. Right, that would be our number z, which we can think of as a vector. You'll study more about vectors in an introductory physics course, as well as linear algebra and Calc 3. What I'm going to do in this course is we're going to focus on doing operations on complex numbers algebraically. However, there's also a geometric interpretation of the operations, which deals with vectors. Before we do that, I said these are like building blocks. So look at the set of integers. The natural numbers. Is every natural number an integer? In other words, if you pick a natural number, would it also fit into the set of integers? Yes, right? So the natural numbers are a subset of the integers. But every integer. So if you pick an integer, is it also a rational number? It is, right? 3 is 3 over 1. So the integers are a subset of the rationals. But aren't rational numbers also real? So the rationals are a subset of the reals. Pick any real number. Is it complex? You say no. Give me a real number. Six. Can I write 6 as 6 plus 0i? And 0 is a real number, so it fits the definition of complex. So the reals are a subset of the complex numbers. What do we think? Is there a number system beyond the complex? Well, that depends on what you think the answer to my question was. So you're saying there aren't numbers beyond the complex numbers? There are. After the complex come the quaternions. After the quaternions would come the octonions. right? There'd be 8 digits, yes. Right, so the complex was like A plus BI. Quaternions are A plus BI plus CJ plus DK. Right, so there's 4. Octonions, there'd be 8 of them. Then beyond the octonions, I think they're called the secternions, where there'd be 16. And in fact, every power of 2 has a number system. Those number systems are well beyond our scope. In fact, you won't even study those for the most part unless you're a math major, with a few exceptions. Right? The higher number systems do have a use when you're trying to rotate space and then rotate higher dimensions of space. But they do exist. And you start to lose properties. So quaternions, you lose commutativity. Octonions, you lose associativity. So all those nice properties that you've been taking for granted when you add and multiply numbers, you start to lose them. But again, that's beyond the scope of this course, so that's more of a Jeopardy type knowledge. Now, I did in number theory. I think I studied them. I only went up to the quaternions. Right. So for the numbers that we're going to be dealing with, you're right. There'd be no complex numbers, right? Every number we deal with in the vast majority of math courses are complex numbers, right? Because for the most part, we deal with reals, but reals are complex. Now, actually, real numbers and complex numbers can be broken down further into 2 categories. We have the algebraic numbers. And algebraic numbers are any number that is the root of a non-zero polynomial, right? So we're going to be studying roots of polynomials starting tomorrow, maybe. If not, Monday. Just basically take any polynomial set equal to 0. The solutions are algebraic numbers. These include every integer, every rational number, and every radical of an integer. So square root of 2 is algebraic. Cube root of 5 is algebraic. Then we have the transcendental numbers. And any number that is not algebraic is called transcendental. The most common number is pi. But square root of 2 is also non-terminating, right? Root 2 is irrational. But root 2 is algebraic. Pi is irrational and is a transcendental number. So if the decimal goes on forever, it's actually it's difficult to determine that just using a calculator, right? Because the calculator only has so much memory, so it can only spit out so many decimal places, right? So yeah, exactly. So if there are 1,000,000 decimal places, but it stops after 1,000,000, that is terminating, right? 100 million. So we call that finite, right? So if there's a finite number of decimal places, it terminates. If it's infinite number of decimal places that does not repeat, then we call that irrational. So again, square root of 2 is irrational. Square root of 3 is irrational. The decimal places are infinite and they do not repeat. Right, but I can show you the problem. And so if I put in square root of 2, and it looks like that it terminates. But it doesn't, right? The calculator just can't put out more than that. Let me just make sure my settings are right. Document settings, float. Yeah. Right. So that's all it can spit out for me. But in fact, these values go on forever and there's no way, right? There's no pattern, so there's no formula to determine the digits after that. Oops, why did I reopen that? I wanted this. And so everything's been building upon itself, right? You should even notice, right? So you remember way back to your math courses in primary school, you started working with natural numbers, right? And then you worked your way up to working with integers. Then you worked with fractions, which are the rationals. And then you finally moved on to the reals and complex, right? So everything's been building up. Now what we're going to do is we're going to work with the complex numbers. So we're going to perform basic arithmetic on it. Uh-oh. So I need to move you and down. There we go. All right, so adding, subtracting, multiplying, and dividing. So I know what you did to get 8. You're only allowed to do that if your numbers are positive. All right, so this property that you used, only valid if A and B are greater than or equal to 0. Right? So first, write them as complex, because they are complex, right? Square root of -2 would be the square root of 2 times I. Square root of -32 would be the square root of 32 times I. And so take root 2 times root 32, that's root 64. Then it's I times I, which is I squared. When you're dealing with complex numbers, you can think of I like a variable x, right? How would you multiply something like 5x times 3x? It might be 15x squared. Same thing here. You just multiply the quote-unquote coefficients and then multiply the variables. So you get root 64 times I squared. Square root of 64 is 8. But what is I squared? Now, I squared does simplify. So look back at the definition of the complex numbers. -1. This product is -8. Okay. And so we first write these in the form of a plus bi. It is 30. Right, we do this problem, we get -3 times the square root of 100. And then times I squared, right? Root 100 is 10 times -3 is -30. I squared is -1. So we get 30. Square root of 100. We will be examining I to the 4th a little bit later. So what is the square root of 100? It's 10, isn't it? And then 10 times -3 is the -30. Why is this not? What's going on? No, that's why I haven't caught up yet. There we go. For I times -3i. Four times -3, -12, right? I times I is I squared. And that's just +12. So what about 6i all squared? Now remember, think of I as a variable x. So if this was 6x quantity squared, what would you get? Right? How'd you get -36? All right, 6i times 6i, you can do it that way. Right? Remember, you can distribute the exponent. So for 6x, the square distributes into each term, right? So it'd be 6 squared times x squared, which is 36x squared. You can do the same thing here. That'll just be 36i squared, which is -36. All right. 2 times the square root of -1 quantity square cubed. Sorry. So same thing. First, write this in the form of a plus bi. Be 2I quantity cubed, right? Root -1 is I. Distribute the cube through to each term. 2 cubed is what? So we'd have 8 times I cubed. Now here's the question. How did you get -8I? Yes. Think of I cubed as I to the 2 plus 1, right? Which is I squared times I. Well, I squared is -1, so it's -I. Right, so that's something handy. Right. Let's look at 3I times I plus 2. And again, think of this in terms of just basic algebra. Distribution. We would have 3I times I, which is 3I squared. Right, then we'd have 3I times 2, which is plus 6I. Right? And then, of course, I squared is -1. So we get -3 plus 6I. What about 3 minus 2I times 4 plus I? Again, think of this in terms of algebra. If this was 3 minus 2x times 4 plus x, how did you expand that out? Sick of orange. Let's change this to green. There we go. What do you mean by distribute? Okay, so that process had a name when you multiplied two binomials together. It's a dreaded four-letter F word. FOIL! First, outers, inners, last. Oh. Phooey. Oh, for Pete's sake. There it is. So what I'm going to have to do is close that and reopen it. So I have no more technological hiccups. Right? So we're going to FOIL this. 3 times 4. Then 3 times I. Then negative 2I times 4. And then negative 2I times positive I. We add like terms. Three minus 8, right? Minus 5I. But then I squared is negative 1, so doesn't that become plus 2? And we get 14 minus 5I. Right? This means that so far there really hasn't been any difference, right, between what we're doing with complex numbers and how we deal with algebraic expressions, right? Like terms can combine. Rules for multiplication are the same. Rules for addition are the same. We still have foiling. Right? We still have distribution. We have the exponent distributing into each term across multiplication. So the only difference is instead of it being a variable x, it's the number I. Five minus 3I times I plus 2. Now again, we're going to FOIL. 5I plus 10 minus 3I squared minus 6I. This minus 3I squared is plus 3, right? 10 minus 3i squared would then be 13. 5i minus 6i would just be negative I. So the answer is 13 minus I. So this bit here, this minus 3i squared, is plus 3, isn't it? It's negative 3 times negative 1. Right, and then plus 10. Quantity of 5 plus 3i squared. Right, well, think back to algebra, right? There are two ways you could go about this. Could write this as 5 plus 3i times 5 plus 3i and then FOIL, right? Or you could use the binomial theorem. Which is the way that I'm going to do it. E5 squared plus twice the product. So 5 times 3i is 15i. Doubled is 30i. Plus the 3i all squared, which would be 9i squared. What is 9i squared? Negative 9, right? Add that to 25. You get what? So we get 16 plus 30i. What about here? Well, let's start with any pair and FOIL it. Remember, multiplication of complex numbers is commutative, so the order in which you multiply them doesn't matter. So you can rearrange this however you want to. Let's just not make things complicated. Let's take the first two and multiply them out. We get 2 times 3 plus 2 times 2i plus negative I times 3 plus negative I times 2i. How does this term simplify? Right? Yes, it's 8 plus I. Now we just FOIL again. 8 times 1 plus 8 times negative 4I plus I times 1 plus I times negative 4I. How does that simplify? Yes, 12 minus 31I. Quantity of root 2 over 2 plus root 2 over 2I squared, all squared. Binomial theorem. Square of the first term. Would be 2 over 4, right? Plus the product, plus twice the product. So root 2 over 2 times root 2 over 2 is a half. Doubled is 1. And then we have that I. That'll be plus a half I squared. Which is, yes, just I. Okay, any day. There we go. Quantity of 1 plus I cubed. Well, again, right, we have two ways to do this. You can write it as 1 plus I times 1 plus I times 1 plus I. And then proceed as we did in number 10. Or we can use the binomial theorem, which is how I'm going to go. And so think back. I think it was the first day which for us was last Monday. I introduced the binomial theorem along with Pascal's triangle, right? Third row of Pascal's triangle. Was 1, 3, 3, 1. By the binomial theorem, 1 plus I quantity cubed. 1 plus 3I plus 3I squared plus I cubed. How is that going to simplify? Exactly. -2 plus 2I. Quantity of 3 minus 2I cubed. I'm again going to use binomial theorem. 3 cubed is what? And then 27 times 1 is 27. What we're now going to have is 3 squared times -2I raised to the first power, which is just -2I. 9 times -2I is what? Now we have to times that by 3. So what is -18 times 3? That's the next term, -54I. It will now be 3 to the first times the quantity of -2I squared. So it'll be 3 times 4I squared, which is what? Okay, I see what you did. I'm going to keep the I squared alone for now. All right, so I'm going to say 12I squared. And then times that by 3. Get 36i squared. Now it's going to be just negative 2i cubed. Negative 8i cubed, and then times 1 is just, again, negative 8i cubed. Yes, 36i squared is negative 36. Simplify this. What do we get? Negative 9 minus 46i. One of the advantages of technology is I don't have to rewrite much. I can just copy paste them and make the appropriate changes. Everything is going to be the same, except, right, all of these minuses here are going to become plus. So it's 27 plus 54i plus 36i squared plus 8i cubed. How's that going to simplify? It'd be negative 9 plus 46i. Oh, sad face, I'm out of coffee. Okay, so for this problem, I'm again going to use binomial theorem. Which means that we need the fourth row of Pascal's triangle. One, 4, 6, 4, 1. First term will be 1 to the 4th times 1, just 1. Plus 1 cubed times 2i, which is 2i, times 4. plus 1 squared times 2i squared. 4i squared times 6. 24i squared. Plus 1 times 2i cubed. That's 8i cubed times 4. 32i cubed. Finally, 2i to the 4th is 16i to the 4th, and then times 1. There's that expansion. What does I to the 4th equal? What do we think? How do you get 1? Right? Think of I to the 4th as I squared squared. That's negative 1 squared, which is just positive 1. So I to the 4th is positive 1. Now, with that in mind, how would this term simplify, or how would this expression simplify? Be careful with cancels out. I think I know what you mean, but it's not technically canceling out. But I am actually going to look at that after we simplify this expression. So how would this simplify? All right, start with the real component first. Be what? 1 minus 24 plus 16, right? So 17 minus 24. That'd be negative 7. Right, and then it'll be 8i minus 32i, right? Which is minus 24i. Before we look at the next problem, right, so we have I. We know I squared is negative 1, right? What did we say I cubed was? And what did we say I to the fourth was? What about I to the fifth? Just be I, right? I to the fourth times I. What about I to the sixth? Right? Being I squared cubed, which is -1. What about I to the seventh? That'd be -I. And I to the eighth? What do you think I to the ninth is going to be then? Goes back to I. Every fourth power, the pattern repeats. But I think that's what you meant by cancels out, right? Yeah, it's not technically canceling out. Right, but it repeats. Which means if I asked for something like I to the 123rd power, write that as I to the 120 times I cubed. 120 is a power of 4. So that's just 1. Right? Here's what I did. Essentially, that is I squared to the 60th power, which is just 1. And then we know that I cubed is -I. So I to the 123rd power is -I. I to any even power either be plus or -1. It's +1 if the power is divisible by 4. -1 if it isn't divisible by 4. Right? And then any odd power of I is either positive I or -I. -I if it is divisible by 3. Positive I if it isn't divisible by 3. Right? So I could have used that here and said, okay, 1, 2, 3. That is not divisible by 3, so it's -I. I'm sorry, 1, 2, 3 is divisible by 3. It's 6. 1 plus 2 plus 3 is 6. I'm sorry. So it's divisible by 3, so it's -I. That is a quick way of simplifying a power of I, a positive power of I. right? Negative 1 plus I quantity to the 8th power. This will be a bit of a pain to do it using the binomial theorem. But can't we write it this way? The quantity squared all raised to the 4th power? Negative 1 plus I squared. Okay, we didn't do it. Be 1 minus 2I plus I squared, right? Isn't that just negative 2I? What is negative 2I all raised to the 4th power? Check your multiplication. $16. 32 is 2 to the 5th. Just 16. Okay. 1 plus I over 3 minus I. So now we're dealing with division. So I need to introduce a new term. So consider a complex number. The complex conjugate of z which is denoted as z bar. Is the complex number a minus bi. So the complex conjugate, when you take the complex conjugate of a complex number, you just change the sign of the imaginary component. Now, why is that important? Right? So when we divide complex numbers, what we do is we rationalize the denominator. To do that, we multiply both the numerator and the denominator by the complex conjugate of the denominator. FOIL the numerator. 3 plus I plus 3I plus I squared FOIL the denominator. You should recognize that. Isn't that the form of the difference of two squares? How does the numerator simplify? What about the denominator? That can simplify, can it? See, 1 plus 2I over 5. This is technically not correct. What's wrong with it? Correct? Isn't that what I have? 9 minus I squared. How is a complex number defined? Isn't it A plus BI? Is this of the form A plus BI? It is? Then what's your A? A can't be 0. If both A and B are 0, then we have 0. It's a very subtle error. That's correct, but this isn't 0, is it? 1 plus 2i all over 5 is not real. This is not proper form. Has to be written as 1/5 plus 2/5 I. Now let me let you in on a little secret. We would typically leave this. In fact, in the advanced courses, that is exactly how I would write it. However, I know for a fact that my open math will not accept that form. So for this course, I am going to write it this way. And I will require you to write it that way, just so we get used to it. Okay? Okay, so continuing on, 1 over I. Remember what we want to do? We want to multiply numerator and denominator by the complex conjugate, which in this case is just negative I. We'll get negative I over negative I squared. Just negative I. Two root 3 plus root 2I divided by 3 root 2 minus 4 root 3I. Multiply numerator and denominator by the complex conjugate of the denominator. All right, FOIL the numerator. 6 root 6 plus 8 times root 9 just 24. Going to be what? Plus 6i. And then 4 root 6i squared. Going to be over 18 minus 16 times 3, 48. 18 minus 48i squared. Numerator should simplify. 2 root 6 plus 30i. Denominator is 18 plus 48, 66. Yeah, that'd be 15 over 33, which is the same as 5 over 11. That leaves us with root 6 over 33 plus 5/11ths I. Any questions on the complex numbers? We're now going to look at quadratic functions. Function of the form ax squared plus bx plus c, where a, b, and c are real numbers, is called a quadratic function. Quadratic functions have two general shapes. right? They're both parabolic, but it either opens upward or opens downward. So the vertex located at negative b over 2a for the x-coordinate, the y-coordinate would be c minus b squared over 4a. Just double check that. Yes. Should have specified. A can't be 0, otherwise it's not quadratic. If A is greater than 0, then the graph opens upward. They can be 0, that's correct. It's just A that can't be. So if A is positive, the graph is opening upwards, and the vertex is an absolute minimum for the function. If A is less than 0, our graph opens downward. And the vertex is an absolute maximum. The graph of f of x is going to be symmetric about the line x equals negative b over 2a. This is known as the axis of symmetry. So we're going to sketch the graph of each of the quadratic functions given. First thing we do is we look, does it open upwards or downwards? Opens upwards, right? A is positive 3. The vertex will be negative b, which is 0, right? Over 2 times a. And then c minus b squared over 4 times a. Our vertex is located at 0, negative 5. Axis of symmetry is the line x equals 0. I also want intercepts. All right, so remember what the intercepts are. It's where we cross an axis. Well, we already have one of them, the vertex. Let's now find out where it crosses the x-axis, which is done by solving f of x equals 0. Your x squared is going to be 5. Means x squared is 5/3. X is plus or minus root 5 over 3. It is not 1-to-1. Quadratic functions never are. Square root of 5/3 is slightly larger than 1. I'm sorry, not slightly larger than 1. It's going to be slightly less than square root of 2, which is like 1.41. I'm going to say this is -5 down there. Probably cross the x-axis right around there. Uh-oh. So something like that. F of x equals -1 minus 1/3 x squared. How does it open? Downwards, right? A is -1/3, which is clearly less than 0. Vertex. Negative. What is B? So it'd be 0 over 2 times -1/3. Doesn't matter because it's going to be 0. C. What is C? All right, it'll be -1 minus B squared over 4 times A. Vertex is located at 0, -1. Axis of symmetry. Once again, the line x equals 0. All right, so just looking at what we have written down, are we going to have any x-intercepts? Why? Exactly. The vertex is below the x-axis, and it's opening downwards. So we only have one intercept. Which is the vertex. So that's -1 there. So I don't know, maybe something like that. Yeah, it's going to depend on all three values. Right? If the vertex is above the x-axis and opens upwards, then obviously no x-intercepts. If it's below the x-axis and opens downwards, then obviously no x-intercepts. Right? But where the vertex is located, of course, depends on the values of A, B, and C. What about here? Right? Opens upward. Vertex. So it'd be negative. What is B? B is not 6. Check the sign. It's -6 over 2 times A, which is, of course, 2, right? What is C? And we just said B is -6. over 4 times a. We get -6, which is just +6 over 4, which is 3/2. This is going to be negative. (36/8), which is 9/2. This means we have 3 intercepts. Before that, let's just write out what the axis of symmetry is. What is the axis of symmetry? It's the line x equals 3/2. Intercepts. Y-intercept first. Right? Y-intercept is easy. Just evaluate f of 0. Before we try to find them, are there going to be x-intercepts? No? Why do you say no? Well, that would be an x-intercept, right? But a quadratic function can't have just one x-intercept. It would have to have either none or 2. We know we're going to have them because this -9/2 lies below the x-axis, right? And it opens upwards. So it is going to have to cross the x-axis. You can factor out a 2x. So we get x equals 0 or x equals 3. So we have 2 intercepts total. The origin and the point 30. Right, there's the origin. Let's say that's 3. Okay, so there's down to -4. Actually, I need to go down to -5. There's -5. That line would be -9/2. So that'd be the y coordinate, and then we have 3/2, right? For the x. Right there. So there's our vertex. Well, start this. This is going to be tough. There we go. So there's that side. Could go through 0. Perfect. Good enough for government work. Probably try to curve that a little bit more. Something like that. Yeah, let's look at this one. How's it open? Right? What is B? And so it's B over. What's A? And what's C? This will be negative 2 over 1, which is just 2. Then we'll get 3 minus 4 over 2, which is 2. Negative 2, 1. What's the axis of symmetry? Right, the line x equals negative 2. We're always going to have a y-intercept. Do we have x-intercepts? Why not? Right, the vertex, the y-coordinate is above the x-axis, right? It's opening upwards. So don't even waste your time trying to find the intercepts because they don't exist. All right, we just do f of 0 to find the y-intercept, which is 3. You'll wind up with no solution. In this case, you'll plug it into quadratic formula, and you'll find that what's under the square root is negative. So you only have complex roots, which means no intercepts. All right, there's our vertex, negative 2, 1. Uh-oh. There we go. All right, so it has to go through that point there. And you're going to have to try and make the other side symmetric. Something like that. That looks kind of good. You'll never get the denominator to be 0, because then it wouldn't be quadratic. Right? In order to get a denominator of 0, your a would have to be 0, right? Which can't happen for quadratic. So you always get a negative under the square root for no intercepts. Yeah, but it might just be easier to do what we've been doing, right, and just analyze it first. How is this quadratic open? It opens downward. Let's go ahead and find the vertex. What's B? Right. What's A? Good. And what's C? Good. 5 minus B squared over 4 times A. We're going to get negative 4 over negative 4, which is positive 1. 4 squared is 16. 4 times negative 2 is negative 8. So we have 16 over negative 8, which is negative 2. 5 minus negative 2 is 7. What is the axis of symmetry? Right, it's the line x equals 1. Again, we always have a y-intercept. Do we have x-intercepts? Yes, we do. Our vertex lies above the x-axis, and we're opening downward. So f of 0 is 5. All right, plug this, or set this equal to 0, solve for x. I don't think that can be factored. It cannot. So quadratic formula it is. Negative b plus or minus the square root of b squared minus 4ac all over 2a. We get negative 1 minus plus root 56 over 4. D6 is what, 8 by 7? And so it'll be 4 by 2 by 7. Be 2 root 14 over 4, which is root 14 over 2. We have an intercept at the point 0.05, an intercept at the point negative 1 minus root 14 over 2 comma 0, and negative 1 plus root 14 over 2 comma 0. Okay, so I need There's 5, so there's that intercept. The vertex was at one's. Oh. Okay. Let's just delete that for now. Make each of these 2. So 2, 4. That's not spaced right. That looks evenly spaced. 6, 8, 10. So 5 would be right here. One, 2, 3. I'm just going to go out that far because I'm at 1, 7. So there's the vertex. All right. Root 14. Slightly less than 4. So root 14 over 2 will be slightly less than 2. So it'd be slightly less than -3. I'm sorry, slightly greater than -3. Say about there. And then slightly. That can't be right. I'm going to cheat. Yeah, okay, so that's about where I have that one. Slightly less than 1, which is what I thought. Uh-oh. Okay, I screwed something up. Oh. I'm an idiot. That was supposed to be +1, not -1. It's -4 over -4. All right, so it's going to be one minus 2 is -1. We're going to be slightly greater than -1. That's going to be like right there. And then 1 plus 2 is 3. We're going to be slightly less than 3. So there. Probably do a better job on that. Enough. X squared plus 4x plus 5. So it looks something like that. Any questions? Okay. So one more thing I want to do. I'm not sure if it's in the lecture video. I'm going to go ahead and derive the quadratic formula. We start by completing the square. So we take half of b and square it. All right, that allows us to do this. All right, do we subtract c? All right, so that equals, I'm going to say it's b squared minus 4c all over 4, right? Just to write it as a single fraction. Take the square root of both sides. Oh, I already royally screwed up. Coffee is starting to wear off. I can't complete the square unless I divide everything by a first. Now I can complete the square. So I need to add a b over 2a all squared to both sides. This term here is now x plus b over 2a squared. Subtract c over a from both sides. Combine them. Common denominator is 4a squared, so that's where the minus 4ac is coming from. Take the square root of both sides. Notice why I can get rid of the absolute value in the denominator. Right? Because this is technically plus or minus a, right? plus or minus times plus or minus is still plus or minus. So it all gets absorbed into this plus or minus here. Now just subtract that b over 2a from both sides. And write it as a single fraction. And there's the quadratic formula. So that's where the quadratic formula comes from. All right, so we've now finished up those two. Okay. Now